So notice that I am already in ionic land. Everything I'm about to talk about is only going to have to do with naming ionic compounds or taking formulas that are ionic compounds and turning them into names. Okay? So ionic land. One thing that you should know by now is that involves charges. So you're going to need that charge sheet in order to make some sense out of what we're about to talk about. It turns out that most ionics are very easy to name, so I'll start off with the easy ones and I'll slowly kind of build a little bit of complexity into the system here. So let's say that we'll switch things up, right? We'll come up with a name from a formula. Let's say that I have a formula that is Al2O3, right? There's my metal. It's an aluminum, right? Let's name it and make sure that even though we might not need it, and it's going to bother people that know this, they're going to say, why are you putting a work area in here? Because I promise you at some point it will help you out of a question, even though technically in this case we don't need this. So what do we got in this box? Well, it's an aluminum. How many of them are there? There are 2 of them. We've got an oxygen. There are 3 of them. All right, so far so good. That makes sense. Now, because we're in ionic land, we got to look up the charge. Aluminum, thankfully, only has 1 charge. It is a 3+. So we're going to put both of those 3 pluses there. We look up oxygen. Oxygen actually has a few different charges. It turns out that the most common charge, according to the periodic table, is 2-. So we're going to put that in there. We look at this, we say, okay, is it true? Like if everything is true, the plus side should add up to the negative side. And it certainly does, right? We've got 6 plus charges, we've got 6 minus charges. By the way, if we were wrong about the charge on oxygen, if it happened to be some sort of peroxide or superoxide, which does exist, our charges wouldn't add up to 6, right? And so it's almost like we're going to use this part of the work area to make sure that this part is doing okay. Same is going to happen eventually where we're going to use this to determine if this part over here that we're working on is okay. So to name this thing, it's going to wow you. Are you ready? This is called aluminum oxide. Whoa! Right? You're like, why did you just go through all this work when all I could have done is just say aluminum and oxygen together and, all would have been done? Well, that is because of the very next problem, what we're going to do. So let's take a look at that. Next example we'll talk about looks a lot like the last one, right? We've still got a metal. It's chromium now. We've still got an oxygen, right? And so let's do our work area and see where I'm going with this. So we've got a plus side of the world and a negative side of the world. On the negative side of the world is my oxygen, so I'll write that out. There's 3 of them. Over here, we've got 2 chromiums now. Okay, and because we're in ionic land, we want to look up the charge and make sure everything is doing okay. We look up, let's say, oxygen first. Right? We look and say, oh, on the periodic table, it's almost always going to be a 2-. So we'll add that in. And as we're kind of going through and checking our work, we look at the charge for something like chromium and we say, uh-oh, there's a whole bunch of stuff listed there, right? And there are a whole bunch of different charges that chromium can take, and this has to do with that kind of weirdness of having d electrons that we alluded to in electron configurations. We don't want to get into all that, like the reasons why, just accept the fact that if you're in the sphincter tightening region, aka the transition metal region, weird stuff happens. One of them is many of these things have multiple different charge states, right? Oxidation states. So we know that there's 2 there, and we're like, well, which one of those charges should I choose, right? 2+ and 3+ is possible. Well, what we're going to do is we're going to use the non-metal side here to come up whatever the overall charge is, in this case 6-. And what we know, if this is a proper formula, is that this side has to have a total of 6+, evenly split between these 2. So obviously, or maybe not so obviously, I don't know, I've looked at this for so long, we have to have 2 3+ charges for this chromium, right? So we know now that the charge on chromium had to have been a 3+. Because if we put 2+ there, right, and we had 2 of them, it wouldn't add up to 6, and we know it had to add up to 6. So what we have here, right, in this situation where we're in the sphincter tightening region for our metal, we have to add something to our name now. And the thing that we're going to add to our name is the charge that is on each one of those cations. And so what we're going to call this thing, right, Cr2O3, is going to be chromium. That one's probably not surprising. With a 3 in Roman numerals next to it, kind of like the Super Bowl, right? You always use Roman numerals with charge, and then we end with oxide. This kind of thing, even though it seems really straightforward, gives students fits, right? This guy right here, that Roman numeral. Sometimes you'll see things with Roman numerals, sometimes you won't, right? It turns out when you see something with a Roman numeral, or when you have to use a Roman numeral, is when there's multiple different charge states for something, which happens quite often on that periodic table, as you can tell when you look at it closely. And so what I've tried to do is, I've tried to, in your lab at least, put little asterisks next to formulas that have to have some sort of Roman numeral. Obviously, if we're going from a name to a formula, which we're going to see in just a second, it's a little bit more straightforward. The thing that we have to do is to recognize that the name, right, that Roman numeral, has nothing to do with the numbers that you see in the formula here, right? A really, really, really common mistake that you're going to make, I promise you, everybody makes it, is to look at a name like this and just kind of say, oh, it's chromium 2 oxide, right? It's not, right? In fact, if your Roman numeral matches the actual number of metals there, it is a total accident and it doesn't happen very often, right? And you'll also notice that I didn't call this dichromium oxide. I can't, right? Because if I call it dichromium oxide, I'm using prefixes and I'm telling people I'm in the covalent land, right? In which I'm not. So you have to be really careful with these Roman numerals. Recognize that it comes from the charge of each individual cation right here. By the way, if there were a question like is going to happen on your lab that says, hey, I've got Cr2O3, what kind of anions do I have in there? What kind of cations do I have in there? Well, what you would say is I have got a chromium 3 cation, or chromium 3 anion, or chromium 3 ion. Frankly, you could also call it that. Obviously, this is the oxide ion. You don't need a Roman numeral with that. That's the oxide anion. And so, this kind of work area, I swear to you, like if you do this for every question, I can't ever screw you up. If we just stay in formula land or stay in name land, I can play with you and just make your brain hurt, and you're going to want to come after me with that trident. So let's see another example, but this time let's take a name and turn it into a formula. Let's say that we have, manganese to chloride. Well, one of the things you'll probably know that I'm going to say is there a metal present? And you say, yes, there is. Manganese is a metal. Not magnesium, by the way. Manganese, it's a different one. It's ionic. We know that because of the presence of the metal. Another tip off to this is that Roman numeral, not always there. So that is telling me a lot about the little work area that I come up with here. Before I'm allowed to do my formula, I look up and see what the formula for manganese is, or the symbol for manganese is. Here, I can already see that I've got a 2+, right? That's kind of helpful to me at this point. If you just remember that the charge corresponds to the Roman numeral. And you go over here to the chloride side. And we have to figure out what the charge on that is. Chlorine has a whole bunch of different oxidation states, but its most common is 1-. So let's put that in there. And you might recognize that my positive side is not equal to my negative side right now. I have to do a crossy trick. When I do that crossy trick, I will end up with a single manganese and 2 chlorides. So there is the answer. But what I want you guys to do every time you come up with your answer is to go back here and make sure that you look at what this entire picture looks like. It'll help you with Lewis structures. I'm just telling you, it's going to help. That's what that formula means, right? And this is what we have. We've got manganese 2 chloride. A couple of things just to beat that dead horse again. Notice that manganese, right? There are not 2 of them. Right? That 2 doesn't mean anything about the number. It has to do with the charge on the element that's on the positive side here of the thing. So let's try out one more example, and then we'll end this video and start another one. So here's a name, iron 3 phosphide. Ask the question, is there a metal present? Absolutely, we got an iron there. So we know that we need to do our little work area and divide that work area up into the plus side and the minus side. You look up the element symbol for iron. It is an Fe. You look up the element symbol for phosphide, and that is a P. Put in your charge. Yay, there's a Roman numeral. That makes my life easier here. There's a 3+. Phosphide, if you look it up on the periodic table, is a 3-. You could either do the crossy trick if you want to and call this Fe3P3, or we could just recognize that iron 3 phosphide is just that. Really is that straightforward. Maybe we'll do one more of a formula to a name, and then we'll call it quits for this video. We've got lead, we've got oxygen, right? What is the name of this compound? We start our work area because we know that there's a metal present. We know that we've got 1 lead, we've got 2 oxygens. Now our job, once again, is figure out what the charge is on these things. You look at your charge sheet, you'll recognize that lead has a couple of different charges, so let's ignore that for the time being. Like we did last time, let's go to the anion, which is almost always going to be clearer. We've got 2- and a 2-. You'll notice the total charge on this side is 4-. There's only 1 lead, so that 1 lead must figure out a way to balance that entire amount of 4- with 1 4+. So this is a lead 4+. Now, because this lead has multiple charges, as you can look on your sheet and tell, we must include that in the name. So this will be called lead 4, Roman numeral 4, oxide. One thing probably deserves just a passing mention having to do with these Roman numerals. Those are the way we do things now, but there are still kind of vestiges of an older system where it's all based on us and ick endings. So like, for instance, when you look this up on the Googles, as I'm sure some of you will do to your own detriment, when you look up the name of something like this, it wouldn't say that it was lead 4 oxide. It would say that it was plumbic oxide. And if you're not watching the video lectures, I'll be able to tell very quickly, or I should say, if you're just Googling answers, I'll be able to tell really quickly. I will not be accepting any of the ick and us type of nomenclature because, frankly, it's just barely used anymore, and we're really trying to get rid of it. So use Roman numerals. Don't use that crazy us and ick system. Be warned.